Hello. So we are studying nonlinear regression models, and so far we considered polynomial model and log model. So they are related to the second part of this analogy. So in both cases, like quadratic, cubic, or log functions have a derivative that depends on x itself. So that was the point. But now we are going to think about the relationship between two regressors. Say the derivative with respect to x1 depends on x2. So it's kind of cross effect. So we are going to consider how we handle when the effect depends on another variable. This is called interaction between two regressors. For example, let's think about the class size, student to teacher ratio effect on the test score. So student to teacher ratio affects the test score, but at the same time we considered percentage of English learners. And then we may imagine that being in a small class would be more effective for some for some students who need special cares like English learners, right? So then the effect is not uniform, but it depends on other variables, other circumstances. So then like we may write it this way: the derivative of test score with respect to student to teacher ratio might depend on percentage of English learners, right? So exactly this is what we considered and like how earlier, and we are going to consider the different cases depending on whether the regressor is binary or continuous. So let's start. Simply, let's start from the Bayesian model where there is no interaction. So this is the standard model. Why the outcome is determined by D1 and D2. D1, D2 are two binary variables, and beta 0, beta 1, beta 2 are parameters. In this case, the effect we are interested in the effect of D1. But remember, D1 is binary. Therefore, it takes only two values, 0 or 1, and we are interested in what if we change D1 from 0 to 1, like turn on the switch. Turn on the switch of D1. Then what would be its effect on the outcome Y? And in this Bayesian model, it's simply beta 1 because it's T2 is irrelevant in the effect of D1. So, but so if it makes sense, then this Bayesian model will work. But as in our previous example, we need to incorporate the effect of D1 dependent on D2. So that is done by including the interaction term. So if the effect of D1 depends on D2, you have to include the multiplication between D1 and D2 and add another parameter beta 3. Then let's see how it what's the difference. So to see that we are going, because we have two binary variables D1 and D2, it is easy to think about the case by case. So there are only four possible combinations, 0, 1 and 0, 1. So there are like at most four different cases. So we will consider all of the four cases. So I will skip this part and let's think about this table. So it is a 2 by 2 table where the columns, the first column denotes D1 equals to 1. The second column denotes D1 equals to 0. And so first row denotes d2 equals to 1, second d2 equals to 0. So there are 2 by 2 cases, and we may evaluate what is the expected value of y depending on the value of d1 and d2. So for example, when d1 is 1, this is 1, this is 1. When d2 is 1, this is 1, this is 1. So beta 0 plus beta 1 times 1 plus beta 2 times 2, 1 plus beta 3 times 1 times 1. So we have to add all of these. But now consider d1 is 0, but d2 is 1. Then this is 0, this is 1, this is 0, this is 1. So because d1 is 0, d1 times d2 is also 0. So 0, 0, we only have beta 0 plus beta 2. So that's our prediction. In this way, just by plugging in 0 or 1 on here and here and here and here, you may calculate the predicted outcome for 4 different cases. Which is straightforward. So and then now we are, as I said, we are interested in the difference between d1 equals to 1 versus d1 equals to 0. So when we change d1 from 0 to 1, how much the expected outcome changes. And the change, there are 2 different changes, the first row and the second row. So that means the effect of d1 can be calculated in 2 different cases. When d2 equals to 1, the difference is a comparison between this and this. So their difference is beta 1 plus beta 3. So this is the effect of d1 when d2 equals to 1. But when d2 equals to 0 in the green box comparison, when you compare in the green box, then the difference is obviously beta 1. So what you see here is that the effect of d1 changes depending on d2. So when d2 is 1 or 0, implying different effect of d1. And then as a result, like from here, beta 3 can be interpreted as the difference in the effects of d1 across d2. So effect of d1 and the difference across d2 is beta 3. This is simple. So if you think about 2 by 2 table, so then interpretation is in particular interpretation of the interaction term, the parameter for the interaction term is difference in difference. So take difference across d1 and then take difference like across d2. So we usually call beta 3 as the difference in differences parameter. So I hope you understand what I'm doing here. So let's think about the example again. So we have 2 binary variables. The student to teacher ratio is simply defined like either 0 or 1. So 1 means large class, 0 means small class, right? Student to teacher ratio is smaller than 20 and greater than 20. And English learners is also classified into two cases. The first group, 1, if the percentage of English learners is greater than 10%, and 0, if the percentage is smaller than 10%. So then and now, we are going to regress the test score on the binary variable of English learners and binary variable of student-to-teacher ratio and their interaction. And our estimates are like given by this. So, and we can apply the same analysis method like this to this example. So now, as usual, we are interested in the effect of being in a large class, say. So I would like to see how much the test score drops if the student to teacher ratio changes from 0 to 1. So from the small class to a large class. And as before, it depends on the percentage of English learners. So the effect of student to teacher ratio should be calculated in two different cases. If the percentage of English learners is 0, then simply the effect is minus 1.9. So the test score drops only by 1.9 points, right? When this is 0, when the percentage of English learner is less than 10%. However, when the percentage of English learner is greater than 10%, then this value takes 1. Then the effect of student to class size, the effect of class size is minus 1.9 plus minus 3.5. So the total effect now becomes minus 5.4 points. So class size being in the effect of class size is larger when the percentage of English learners is higher, which is what we expected without looking at the data, and it makes sense. It's intuitive. So it is not statistically significant. The beta 3, the coefficient of the interaction term, is estimated to be minus 3.5, but the standard error is quite large, 3.1. So this coefficient is not significant. Therefore, statistically, we say that the interaction effect is like not significant. However, if you ignore the significance, the estimation results is consistent with what we expected. And in more detail, in particular, if you calculate the expected test scores, you have these low student to teacher ratio, high student to teacher ratio, low English learners, low percentage of English learners, high percentage of English learners. You can calculate the predicted test score for each of the 4 groups and calculate the difference between low student to teacher ratio and high student to teacher ratio in each case, and then calculate difference in differences. That is 3.5. You will find 3.5 by taking the differences. So this is the simplest possible example of interaction term. So it is widely used in many applications, and as you can see, it makes very much sense. So the main idea of this chapter is that the effect of a regressor is not constant. So it may not be constant. Then you need to think about nonlinear models or interaction terms, so that your regression fits the data better and you can interpret the results better. So that is the main theme in this chapter. And time is almost up, so I am going to continue. I'm going to continue in the next one. So see you later.